Hello and welcome to a video, this time going through Step 2, 2014 Question 6. Now, sorry I've already got the writing on, it's just that I went halfway through the video and then had a problem, I had to stop it. So this is, I think it's actually my third attempt at doing this video, so I'm going to go through this quite quickly, but I'm going to mention hopefully a few useful tips as we go. Okay, it starts off and we've got to prove this result. Anybody who's done the first chapter of the second book on complex numbers in further maths might want to use de Moivre's theorem to prove this, but it's actually far easier doing it in the way they've suggested. So you could, but just saying, because they've said by simplifying this or otherwise, the otherwise approach, well, one of them anyway, is to use de Moivre's. There's probably other ways of doing it, but this is a very sensible suggestion. So we'll simplify this. Seems pretty obvious to use compound angles, so sine rx cos x over 2 plus cos rx sine x over 2 minus sine rx cos x over 2 minus cos rx sine x over 2. Everything cancels and you get 2 cos rx sine x over 2. So it's pretty easy to simplify that. It's not so obvious though why that helps us deal with this. The only thing which occurred to me was that cos rx in here, well, r could act as a counter then for 1, cos 1x, cos 2x, cos 3x, cos 4x. So what I did was I rearranged this slightly, this identity, to make cos the subject. And I've swapped r's for n's here just to make the next result a bit clearer. So cos nx is going to be that, and I've changed the r's for n's and I've factorised back out the x just because I thought it would be slightly nicer looking like that, and then I've divided by 2 sine x over 2. So I've got this. So how could I use this? Well, if I use this, I get what's called a telescoping sum, which is just a sum where the middle terms cancel. Now, cos x is obviously, well, n is 1, so we've got 3x over 2 there, and x over 2 on the back, and it's over 2 sine x over 2. Plus, okay, when n is 2, you're going to get sine 5x over 2 minus sine 3x over 2 over 2 sine x over 2. When n is 3, you're going to get sine 7x over 2 minus sine 5x over 2 sine x over 2. All the way up to the last term, which is just going to be sine n plus a half x minus sine of n minus half x over 2 sine x over 2. Now you can see I've already started crossing out the terms which cancel, because if we just zoom out a bit to see that expression, it is in full. This term is going to cancel with, where is it, this term over here. This sine 5x over 2 is going to cancel with the next minus sine 5x over 2. The sine 7x over 2 is going to cancel with a minus sine 7x over 2. You're going to be left with a minus sine x over 2 at the start. You're going to be left with, because that sine m minus a half x is going to cancel with the previous positive sine m minus a half x, you're going to be left with sine m plus a half x as well. So you've got sine m plus a half x minus sine x over 2 sine x over 2, which is, I hope, the result that they've asked us to establish. Yes, it is. Okay, so how have they tried to confuse us next in this question? Well, they've used just a bit of sigma notation. That often freaks students out. You want to get comfortable with that though. And I've always advised students with sigma notation, just write down the first few terms so you get an idea. So I've written down S3 of x. Now, you might want to get used to the subscript kind of notation as well. S3 is just where n is 3 over here. So you're adding up the first 3 terms. So it would be sine x, because r is 1 first, plus a half sine 2x when r is 2, plus a third sine 3x. And I've just given you that as an example, because they want us to find the stationary points on S2 of x. Well, S2 of x is just going to be the first 2 terms, sine x plus a half sine 2x. Okay, find a stationary point. So differentiate this, you get cos x plus cos 2x. Set it equal to 0. And then what we're going to do, and I haven't written this down yet because this is how far I got in the last video, is I'm going to use double angle for that. Seems fairly sensible. So double angle for this is 2 cos squared x minus 1. And we've got a quadratic. And so I'm going to factorise it. And I presume it factorises because it's told me to find the coordinates, and sketch the function. Sure enough, it does factorise to give you that. And so you get cos x is a half, or minus 1. And if you're just dealing in range from 0 to pi, that only gives you pi over 3, or pi. So now we can sketch it. Have a look at the original function. The original function is sine x plus a half sine 2x. That's what we're actually sketching. Clearly when x is 0, y is 0, we've got a turning point then at pi over 3. And by the way, if you plug pi over 3 back in here, you're going to get root 3 over 2 there, a half times root 3 over 2 here, because sine of pi over 3 and sine of 2 pi over 3 are the same, because sine of pi minus x is identical to sine of x. So you're going to get root 3 over 2 plus a half of root 3 over 2, and that sounds to me like it's going to be 1.5 root 3 over 2's, which is 3 root 3 over 4. And by all means do that on a bit of paper. I've already worked it out. I'm not doing it all in my head. I've done the whole question now. Okay, and so then we've got another turning point at pi. Maybe I should have written down the coordinates afterwards. Pi over 3, 3 root 3 over 4. You can work that out. It's pretty straightforward to do. And this is pi, but when you plug pi back into this, you get 0. Yeah? And so that's what that's going to look like from 0 to pi. Just turning into a stationary point there. Okay, so we've done part 1. Part 2, show that if Sn of x has a stationary point at x equals x0, then this holds. Okay, well, what is Sn of x? Sn of x was defined by the sigma notation to be sine x plus a half sine 2x plus a third sine 3x and so on and so forth until you get 1 over n sine nx. And if I'm going to find the turning points on this curve, I'm going to differentiate it and set it equal to 0. Now, this is what's really nice about this. You can immediately see how it links to the first part. Isn't that rubbing out? Okay, you're going to get cos x here. You're going to get cos 2x there, because the 2 is going to spring out, cancel with a half, but be left inside. And at the end, you're going to have cos nx. In other words, you're going to get exactly what they had at the start. And so if this equals 0, well, let's just use that result we proved at the start, because it's bound to be useful. I'm going to immediately rewrite this as sine n plus a half x minus sine x over 2. All over 2 sine x over 2, I think it was. Oh, but because they said to me at x0 there's a turning point, I'm going to make this x0, yeah? And then we know that we're dealing with the turning point they're talking about, because we're showing that if it has a stationary point at x0, then this result holds. Now, looking at that, they need a tan involved. I'm going to times that across and put that on the other side first. So I've got sine of x0. Sorry about my x's, they're getting really bad. It's because I'm slightly frustrated with the video problems I've had with this. I use a piece of software called Kazam, and it's been letting me down recently. So I've times that over there, and I've added that over there. And then, like I say, they had a tan involved, so divide by cos x0 over 2. Now, you need to be very careful when you divide by something like this, because could this equal 0? Well, as 0 is less than x is less than pi for this question, this part of this question. Check back in the question, you'll see what I mean. X over 2 is between 0 and pi over 2, and so cos, and x0 is what I'm interested in, cos of x0 over 2 can't be equal to 0, yeah? And that's why I can safely divide by cos x0 over 2. Now that's going to give me tan x0 over 2 on this side. And on this side, well, let's actually expand that using compound angle formulae. You're going to have sine nx0 plus sine x0 over 2. And then I'm going to be putting that over cos x0 over 2. Yeah? Okay, so what have I got here? Well, that's simply going to be, if we simplify the top, oh, hang on, what have I just done there? That is the, I'm laughing, that is so bad. Let's use compound angle formulae properly. I think I was just trying to point out that I've times this into the brackets, that's it. That's what I was trying to show there. Now let's use compound angle formulae. So we're going to have sine nx0 cos x0 over 2 plus cos nx0 sine x0 over 2. Be careful with your arguments. Don't get lazy not writing them down. Oh, I am writing. Okay, now we're almost there. And do look where you're going. I'm not looking where I'm going because I've already done this question. Here, the causes cancel. Trust me, though, I did when I was doing this. And here it turns into a tan. Yeah. So there it turns into a tan. And now you can easily rearrange that into their result, which has sine nx0 as a subject. So let's just write down the final result. I need to invest in a better graphics tablet. Okay, it's 1 minus cos nx0 multiplied by tan of x0 over 2. Okay, there we go, as required. Now, the next bit is where the question gets really quite difficult. You've got to actually prove, 1 second, sweetie, I'll be in for burgers in 1 moment. You've got to prove that s subscript n x subscript 0 is greater than or equal to the previous one, s subscript n minus 1 x 0, using this result. Yeah. Now, this wasn't too bad. It was the next bit which really I thought was the trickiest bit. So what can we do? Well, sine of n x0, let's just write that out. Sorry, not sine, but Sn of x0. Let's write out what this actually means. It's sine x0 plus a half sine 2x0, yeah, all the way up to 1 over n sine nx0. That's what that actually represents, yeah? Now, Sn minus 1 of x0 is very, very similar to this. In fact, it's only going to go up to the preceding term, and then this one's just going to have that extra term on the end. So let's just put it like this. So, Snx0 does actually equal, if you like, you've got this just before the last term, that's Sn minus 1 of x0, isn't it? Yeah, so you're going to have Sn minus 1 x0 plus 1 over m sine nx0. Now there's a reason they made that in this sentence, there's a reason they made sine nx0 a subject. It's so you can safely plug it in here. And so let's do that. Remember, that's positive 1 over m, and then we've got a 1 minus cos nx0 multiplied by tan of n, or x0 over 2. Now, all we've got to do now, if you think about it, is convince ourselves that that's a positive term, because then that will definitely be greater than or equal to that if this is 0 or bigger. Yeah? And so that's what I need to prove now, that this, if I can just underline it, I've got to prove that that is positive, because then Sn of x0 is definitely greater than or equal to Sn minus 1 of x0. So let's try and do that. Okay, that's not too hard actually, because if you just think of your trig, yeah, we know as 0 is less than x0, which is less than pi, well then pi over 2, let's not use less than or equal to, x0 over 2 is going to be less than pi over 2, and so straight away I can see why the tan term, I apologise, I need to get better at graphics tablet, I think. Okay, so if this is true, then tan, well, that's definitely positive from 0 to 90, and so I can say that's greater than 0. As for 1 minus cos nx0, I can say, well, that's definitely between, just like cos of stuff is always between 1 and minus 1. Now, this could be equal to it, because we're doing n times x0, n could be like 1,000, so it's not restrained by this. But what I can do straight away is I could times it all by minus 1. Now, I hope you don't mind me just straight away figuring that that's the same as that. I hope you've seen this in maths classes, that the reason that happens is because you times it all by minus 1. That becomes 1, that becomes minus 1, that becomes minus, but these all change round, which can be then be rewritten backwards like that. And then add 1 to it, and you can see that this is actually trapped between 0 and 2. Cool. Okay, now I've done enough. So 1 over n, 1 minus cos of nx0 tan of x0 over 2 is definitely greater than or equal to 0, and hence Sn of x0 is greater than or equal to Sn minus 1 of x0. Marvellous, yeah? We've now proved that bit, yeah? Did you say if Sn minus 1 of x is greater than 0, then Sn of x must be greater than 0 in that interval of 0 to pi? This was the bit which I found toughest, but I then realised what they're getting at. It was kind of just abstract and confusing to me, but okay. What have we shown so far? We've shown that the turning points for Sn must be greater than the y-coordinates of wherever the x-coordinate is for that particular turning point in Sn for Sn minus 1. So take a quick sketch. Yeah. Let's draw Sn. Now remember, let's note right at the start of this that Sn of 0, if x was allowed to be 0, Sn of 0 would be 0 because it's just sine of 0 plus sine of 2 sine of pi plus sine of 2 pi plus sine of 3 pi, a third sine of 3 pi, so on and so forth. And multiples of pi in natural numbers are just always 0 for sine. So that's true. And oh, sorry, you just end up with zeros, and then it's on the next one when you plug in pi, you also get 0. Yeah, that's going to be really useful to me because for sine, if I was to sketch y equals Sn of x, well, Sn minus 1 of x, using the fact that they told me it's definitely greater than 0, I know that maybe it does something like that, but I know it definitely finishes off at 0 and starts at 0 when x is 0 and when x is pi. Now, what about Sn? Yeah, well, Sn, wherever it's got its turning points, they must be higher than this, yeah? So maybe it's got a turning point there, and it doesn't necessarily line up with that turning point. Maybe that's your first x0, yeah? But there might be other turning points for this bit, and what we're saying is, if this has another turning point, then it must be at least equal, but possibly greater than, but whenever it turns, it must be less than or equal to that other function there. Let me just finish it off. Yeah, maybe it goes something like that, yeah? So what does that show us? Well, all we really need to argue is, let me put it like this. If Sn of x was less than 0, then it must have, yeah, bearing in mind it starts and finishes at 0, yeah, it must have a turning point, a negative turning point, yeah, because it starts at 0 and it gets back to 0. When I say a negative turning point, I mean a turning point where the y-coordinate is negative. Can I make that very clear? Yeah, and I'll try and make this clearer than what I'm writing now in my notes. My solution looks a lot nicer than this, the one I've written up. So if Snx is less than 0, then it must have a negative turning point. In which case, Sn minus 1 of x has a negative turning point. Now, why can I say that? I can say that because Sn of x0 is going to equal to Sn minus 1 of x0, which is another way of saying these turning points are always greater or equal to these turning points. The y-coordinates, I mean, of these turning points, they're always larger than the y-coordinates of these turning points. But this would mean that this would have a negative turning point. And that contradicts Sn minus 1 of x is greater than 0. Yeah, that's saying that the y-coordinates are always positive, yeah? So it's impossible. Okay, so what have we proved now? We've proved that, yeah, and then I'm just going to say, hence Sn of x. Then can I just finish off my argument? Hence Sn of x is greater than 0, yeah? This is basically a proof by contradiction. I'm saying if it was less than 0, whilst can I just point out here, whilst 0 is less than x is less than pi, because those were the original conditions on showing that the Sn of x0 is greater than or equal to Sn minus 1 of x0. Okay, now once you've done that, last part is dead easy. It's crying out for induction. You've basically done the inductive argument in the last part, because you've just got to show that S1 of x is greater than or equal to 0 in this range, and it is trivially so. Yeah, so inductive proof. Yeah, base case, S1 of x equals sine x, yeah, which is obviously greater than 0, yeah, whilst you're in that range, yeah, it's strictly greater than 0. So the result holds. My writing's, I'm just going to try with a blue pen. Yeah, that's much better. Result holds for n equals 1. Yeah. Now let's assume true for n equals k, i.e. s little k of x is greater than or equal to 0. And I think they're doing greater than or equal to 0 here. Let me just check, because you're going to be precise. Yeah, sk of x is greater than or equal to 0 for 0 to pi. Yes, I shouldn't be using strict ones in that first bit of my proof. I should be using those. Yeah, and it's obvious for 0 and pi, you know, it's pretty obvious. Whilst 0 is less than or equal to x is less than or equal to pi. Okay, then, as proved above, sk plus 1 of x is also greater than or equal to 0. See above. Hence, by induction, the result is established. And you could just include your inductive remarks there. I'm just going to get this video finished, but just to quickly describe my inductive remarks here, because you will lose marks in the exam if you don't say it properly. But we've shown the result is true for n equals 1, and we've shown also in part 2 really that if the result is true for n equals k, then it must be true for n equals k plus 1. And as the result is true for n equals 1, and if it's true for n is k, it's true for n is k plus 1, then it follows by induction that it must be true for n is greater than or equal to 1. And there we go. Okay, hope you enjoyed that video and it was useful. Keep up the hard work on STEP.